So here is my attempt to explain to you what derivatives and integrals are in a conceptual way without too many numbers involved. So we have a function here, it's just a polynomial function, just a quadratic function with the equation you can see right here. And we have a point P on that function, which we can just move around like that. So first of all is the derivative. What is a derivative of a function? By now we should be confident with our understanding of this. The derivative just refers to the slope of the function at any point. So for example, if I'm down here, the slope of the function at this point is going to be 2.66. And we can visualize that just by activating the derivative here. So that blue dotted line represents the derivative. As we increase p, the slope of our derivative is going down. It's getting less and less steep. And then when we get to this point here, the slope of the derivative is going to be horizontal, and then the derivative starts to go negative and gets more and more negative as we go. We can graph that derivative. If I activate this right here, this is just the graph of the derivative. See, if it's just f prime of x, and it's only showing us up to p. So as I increase p, it's gonna reveal the derivative. So again, we said positive slope here, and it's a pretty steep positive slope, which is why our value's up here. But as we go, our slope is going to decrease, 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 decrease. And then eventually, again, the blue line here represents the derivative. When we get to this maximum here, the slope is 0. So the derivative, the graph of the derivative is going to be 0. And as we continue, the slope starts to get negative and negative and negative. So as we'd expect, the derivative of our quadratic function is a linear function. And that's what we could see there. I can remove this condition here, and we can just see that that's the whole derivative function there. It's just that line like that. So that's the derivative. We're pretty confident with that. So let's hide that for now, and I will hide that line as well. Now what we can think of is going the other way. So we just found the derivative of our function f of x. But what if f of x was the derivative of another function? So what if this here represented the slope of the tangent of another function? So think about that. What are some critical values here if this represented the derivative of a function as opposed to the function itself? Well, where is the function, the original function, going to have a slope of 0? Well, it's where this function is equal to 0. So right here we would expect that function to have a slope of 0. And over here we'd expect that function to have a slope of 0. So horizontal tangents for our function at here and here. And then if we think about it like this, all the way down here, our function is going to have a negative slope because we're down here, we're in this quadrant here. And then as we pass the 0, now our function is going to have a positive slope. So just thinking about it like this, we're going to have a negative slope. So just tracing with my mouse, we're going to have a negative slope, and then the slope is going to be 0, and then it's going to be a positive slope, and then the slope is going to start to, well, it's going to still be positive, and then we're going to get to this point here, and the slope is going to be 0, so it's going to plateau, and then it's going to have a negative slope past that, so it's going to come down. So we'd expect it to be some sort of cubic function with our maximum and minimum values, our local maximum and minimum values at these 2 points here. Okay? And we can actually reveal that. So I'm going to reveal that like this. There we go. Now, if you notice, what I did is I wrote out the function like this with a whole bunch of fancy symbols. Don't worry about those so much for now. But what I want you to think about is this graph right here. And it's sort of as we said, right? It has a minimum down here where the slope of the function would be 0. And it's got a maximum here where we said the slope of the function is going to be 0. So that all works out. But one thing to ask yourself about this, is this necessarily the only function that it could have been, that could have had this derivative of the quadratic? And the answer is no, because this derivative here doesn't tell us anything about where the graph starts. So we could actually move, we can shift this whole function up and down, and the derivative still applies, right? So if I move this function down, say, to have a y-intercept of -2, let me just go down there. This derivative function still applies because we still have a slope of 0 here and here. We still have a positive slope in between these two values, and we still have a negative slope down here and down here. So we don't actually know where this function is. All we know is that that's the general shape of it. So that's one of the characteristics here. When we do this, we have to keep that in mind. Now, another name for this, for going sort of backwards and finding the function that has the derivative of something, we call that taking the integral of it. So the derivative is when you find the slope of a tangent of something. The integral is when we find something that has a slope of a tangent of this curve. Another way to call it is the antiderivative. Okay, so it's the opposite of the derivative. And integral and antiderivatives are same thing, technically. So that's basically what this line is, and that's basically what an integral is. And there are a whole bunch of tricks to basically take this function and find the function that would give this as its derivative, and that process is called integration. And we're not going to do that process here, because I want to show you one more thing. So that's what the integral looks like of this function, right? It's this shape. But what I want you to think about now is this weird, crazy, sort of cool fact about integrals. So we talked about one way to find the integral is to find the function that would give this derivative. But there is another way to find the integral. So I'm going to start my point at 0. And I'm actually going to change this function. And I'm going to change this function to only show us up to p. So between 0 and x and p. So you'll notice as I increase p, it's going to show us what that function is. There's a good reason for this, and I'll show you in 1 second. Now I'm going to activate this integral right here. Another way to think about the integral is that it's the area below this curve. So it's the area between this curve here and the x-axis. And we can visualize that, because I activated it here, by moving p over. So as I move p over, the area between the function and the graph is going to increase. Let me actually hide this for a second just to show you what it looks like. So we're talking about the area between 0 and the x-axis and p. So you see we sweep out this area as I increase p. And the function actually, the integral of the function actually represents that area as well. So again, let me turn that function back on, the integral. So as we move p over, you see the area, the red area, is increasing, 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 which is why that blue line is increasing, increasing, increasing. And still increasing, increasing, increasing. As we get to this point, so we've swept out this entire red area, and this entire red area has an area of about 4.87, as you can see here. And if you look on the graph, it's almost at 5. So integration is just a way of finding sort of this area below this curve. And if we keep going, what's going to happen is we continue along the curve. But you'll see the integral, the area, actually starts to decrease. And that's because this area here counts as a negative area. So we basically have this big positive area here and this negative area here. And that negative area is taking away from the positive area. And it keeps on going, keeps on going, keeps on going. And eventually the total area between the two of them, so actually right here, if we look at our number over here, right, our areas are getting very close to 0 if you add them up, because essentially this area here is equal to this area here. So that would be 0. So going back here, that's basically another way to look at what an integral is. So again, just to recap, one way of looking at what this integral function is, let me just take away this whole thing here. One way to look at what this integral function is, it's the function that would give us the derivative of this green line here. And another way to think about it is the area below the green line. It's crazy that those two things are equivalent to each other, but they are. Let's talk a little bit more about a different type of integral. So this is one type of integral where we're basically starting at 0 and we're increasing, and that works. But you don't always have to start at 0. Our integral can start and finish anywhere. And this is actually very useful, has a lot of applications. So I'm just going to hide that integral there, I'm going to hide that integral there, and we're just going to actually forget about p. I'm going to hide p for a second. Okay, so we have, let me turn off the label, I don't want p to be there at all. We have also what's called a definite integral. And what this is, it's just the area between two values. So if I wanted the area between of the curve between 1 and 2, we would take the integral between 1 and 2. And that's actually what this means down here. If you look at this notation, essentially what this means is we want the integral, that's this long S shape here. That just means integral between a and b. So that's sort of the range of your integration of the function f of x, so the green line is f of x, and then the dx at the end just represents that we're taking the integral in terms of x, with x as our variable. So that just always needs to be there. But basically what this is telling us is that the area between 1 and 2, the area of this red shaded region, is 1.98. It's about 2. And if I change this, now the a is different, so now this area has increased. And I change it here, our area increased. So now our area is about 4. And that's basically, that's called the definite integral. And this is very, very useful because a lot of times there's a lot of applications of functions that represent the area below the curve. For example, if you wanted to find the amount of work done on an object, the amount of work done on an object is equal to the force, the area under the force displacement graph of that function. So in order to find the area under the force displacement graph, you essentially need to integrate, unless it's a really simple shape that you can just find the area of. But a lot of times it's not. So you can see we can find the area between any 2 points. Notice also, if we switch it, so we're finding the area, the integral between a and b, or the area between a and b. If I switch it, reverse them, I'm going to end up with a negative area. See that? Because I've switched this. I'm still taking the area between a and b, but because I've switched it ends up being a negative area. So anyways, oh, and then one more thing. So I can bring this over here, and remember how I talked about last time, if you have it below the axis, that's going to be a negative area. So here, now a and b, this area down here is considered a negative area and has a value of about 0.9, negative 0.9. So that's essentially what an integral is. It's the area below the curve. But again, there's another way of thinking about it. It's just the function, the derivative, the function that would have a derivative equal to that green line. So that's what an integral is. Stay tuned for another video on how to calculate the integral of some of this stuff and how to solve some problems with that. I will make this, this Desmos file available to you in the comments.